Hello everyone, thank you very much for coming to our talk. I'm Finian and this is Ollie and we're students from the UK and we've got some pretty cool demos to show you now. So I'm going to hand you over to Ollie in a minute and we're going to just run through the menu real quick. So we're going to give you a very quick introduction to machine learning and what we wanted to achieve with it, how we did it and what our next steps are going to be. So over to Ollie to give you a quick introduction on what machine learning is.
Okay, so machine learning, the basic principle of machine learning is that a program can adjust itself in order to learn how to do something. There's loads and loads and loads of different applications of this in industries. So, for example, you have OCR, which is optical character recognition, which allows your letters which you give to the post office to be delivered to the correct address. In addition to this, they're used in agriculture, so farmers can find optimal times to sow their seeds and do other things around their farms to maximize their profits. You see an emergence in the medical industries where more and more, not doctors are being replaced, but they're using machine learning to diagnose patients more effectively. Hello? Yeah, than doctors would do otherwise. It's used in the financial industries, so for stockbrokers, they use it to predict fluctuations in markets and how they can capitalize off of it. And as well as this, it's used in logistical companies. So, for example, transport and delivery, they use it to predict how demand for their service will change depending on different factors. Next I'm going to introduce what a fully connected neural network is. It's the most basic form of a neural network whereby all of the outputs of the previous layer are connected to all of the inputs of the next layer by weights, and data propagates through the network, as we can see. There are some problems associated with fully connected neural networks, however, when you're dealing with large-scale images. So, for example, with a 10 by 13 image, if you have a standard fully connected neural network, you'll need to learn over 6 million parameters to just run that small image. If you then upscale that to a medium resolution 600 by 800 image, you need to learn over 1.4 trillion weights. This is obviously a problem because that amount of data can't be stored on one single computer, and so it's impractical for image analysis. Enter convolutional neural networks. So convolutional neural networks are another form of neural network whereby a filter of weights is slid across the input map, and it creates output maps accordingly. This differs from a fully connected neural network whereby you share weights across the layer, which means that you can reduce the number of weights which you have to learn. So with a convolutional neural network, depending on what size of the image, it doesn't actually change the number of weights which you need to learn. You only learn the number of weights which you have in your filters. So for example, with a 10 by 13 image, we need to learn 4,608 weights for a similar output, which is a dramatic decrease from what we had with the fully connected neural network. Then with the same 600 by 800 image, we still use the same number of weights because we don't change the network structure, we just increase the size of the input. Convolutional neural networks are trained like every other neural network, whereby you give them an input and an output, and they adjust themselves to output a more accurate value to what you specified. These convolutional neural networks perform much better in image analysis as well by their nature.
So the end goal is to colorize a black and white video. What's a video made of? It's frames, okay? So the first thing we have to do is extract all of the frames, a whole set of photos, and the first step is to figure out how to colorize a single picture. So that was the first thing we needed to do, how to turn a black and white photo into a color image. Then we'd expand on that and do that for all of the frames and stitch them back together into a video. The current approach to doing this isn't practical. You can pay 400,000 euros for a 2-hour blockbuster and they'll do it for you. Or you can do it with machine learning completely for free.
So how do we do this? What we did was we take the black and white video and we split it up into black and white frames. Then what we do is we colorize each one of these frames to produce a colored frame, and then we stitch them all back together again to create a color video. So we tried 3 implementations of this. The first implementation was a custom solution, whereby we wrote our own convolutional neural network in C++ and OpenCL. This took a long time to implement because we had to understand and learn all the maths and the underlying principles around it. And then when we tested it in relation to other frameworks, we found that it was slightly slower. The next approach was to use Tensor Flow, which is Google's solution to machine learning. Tensor Flow is easy to use, it's optimized for the GPU, and out of the box it comes with distributed machine learning by default. You can use this Docker command if you wanted to have a go with it and apply yourselves. The problem which we found with TensorFlow is that it took way too long for us to train the network so that it colorized the images. So we wouldn't have had it in time for this. So we had to go with a third approach, which was to use Caffe. Now, Caffe is a lightning-fast implementation of convolutional neural networks, and it was developed at Berkeley. And we used some research done by Richard Zhang, who's also his incredible research. But Richard Zhang, who was from the University of Berkeley, had developed a model, a pre-trained model, which we used in conjunction with Caffe.
So there's some problems with machine learning, but the main one is it takes an awful long time to do anything. If you're training a model and it takes 7 days, your development cycle is 7 days. Okay, you change your code, you run it for a week, and you come back, oh, it broke. That's not very useful, really. So we had to combat this somehow, and one of our main problems with hardware, our laptops weren't really fast enough to run this. We also found that you can't do your homework whilst you're doing machine learning because your computer locks up. And we also had very limited access to GPUs. We obviously have them in our laptops, but they're not fast enough to make any real difference. So our solution to this was Packet Host. We got in touch with them, and they very kindly gave us access to some of their servers to run our networks on. So thank you very much to Packet Host. Another thing we thought about trying was Nvidia Docker, which gives us access to the GPU inside of Docker containers. We thought this would be really useful to run with TensorFlow with a distributed network. But the GPUs, as I said, that we had access to weren't fast enough to make this worthwhile, so we decided we weren't going to do this. So now we've got our model that works on colorizing images. How do we do this? We put it in OpenFaz. OpenFaz is an open source framework for running serverless functions developed by Alex Ellis and a whole bunch of other contributors. It makes it super easy to take essentially your code, put it in a function, and scale that up backed by Docker Swarm or Kubernetes, right out of the box. It's really easy to do. So what does our stack look like? Well, on the base, we've got Docker Swarm, and we have a service deployed on Docker Swarm called a tweet listener. And basically all that does, it looks for tweets matching a certain criteria that have an image. When it gets a tweet matching that criteria, it feeds it into our first OpenFaz function, which is called colorize. It colorizes the image and then feeds it into our last function called tweetpick, which then sends the colorized image back to the original tweet. So we're going to give you a demo of this right now. So I'm going to switch out to Chrome. And I'm going to tag @colorizebot. Upload a black and white image, as you can see. And now I'm just going to tweet this image. Wait for it to upload. And what this is going to do is our tweet listener on Docker Swarm is going to catch this tweet coming through, and it's going to drop it down through the OpenFaz functions, and we should get a reply within about 10 seconds on our Twitter feed. So once that uploads. Okay, so if I go over to notifications. Thanks for the tweets. Okay.
Did it end?
Okay, what I'm going to do is I'm going to go to the bot's account, because it looks like we're triggering the spam filters again. Oops. So if I go in here, oh, Alex tweeted for us. Great, thanks, Alex. There's our tweet, and there's Alex's tweet. So they came back, and it took just over 5 seconds to process the whole tweet. So it does work, and we are going to give you something even cooler now. I'm going to switch back to this. We want you to try it right now. Get out your phones, find a black and white image. If you don't have one, go and Google one, and go and tweet it right now. Don't forget the hashtag DockerCon. When you've got your reply, just put your hand up so I can see that it's all coming through. And OpenFaz is integrated with Prometheus, which means we can do cool things like this. We can back it with a Grafana dashboard and see in real time all our analytics going through the functions. So I want you to max out that graph up the top there. Get tweeting. Okay, we've got some coming through. Thanks for that. So we're currently going at, what's that? Just under 2. Yeah, keep going, keep tweeting. Yeah, you got one? Nice. Anyone else? Got one up the back, 2 over there. Cool. This is all backed by OpenFaz, and it'll be auto-scaling that for us. Say again, sorry? Yes, you need to tag @colorizedbot in your thing, because otherwise we trigger Twitter's anti-spam. Okay, cool. Right, now I'm going to hand over to Ollie, who's going to show you something pretty special.
Okay, so we've proven that we can colorize a single frame, but our original aim was to colorize a video. So we took a 20-second cut from Alfred Hitchcock's trailer, Psycho. Oh, is it working? Was it not working? Come on.
How do we play the video?
Wait.
Oh,
done.
Great.
Oh, no.
Yeah, the video is embedded in the presentation.
Do you have it downloaded on the computer?
Yeah.
You could move that onto that one.
Here we go.
Yeah, so this is the colorized, part of a colorized trailer for Alfred Hitchcock's Psycho. We took over 5,000 frames of the trailer, and we colorized each one of them independently. Then we stitched them back together again to create the trailer, which we can see from here. So, how do we go back to? Okay, so we can see that the output is good, but it could be better. And so we've come up with a couple of ways which we can do that. So the first way which we want to do it is we want to use recurrent neural networks to improve the quality of the output. So a recurrent neural network is another form of a neural network where the output of the previous frame will influence the color of the next one, so you don't get disparities between frames and the occasional bit of flickering. As well as this, we wanted to run a Gaussian blur through the output so that we would also improve the quality of the output. And then also what we wanted to do is we wanted to run it on GPUs to decrease the time spent in the development cycle.
So thank you very much for listening. If you have any questions, we'd be delighted to answer them, or you can come and speak to us after the talk. Thank you.
Yeah, cool. Thanks, guys. I think Skynet is upon us. Machine learning is the future. Questions? We have like 5 minutes even.
How is the impact? Hi, congratulations for your work.
Thanks.
How is the impact of putting many colors in a single image in the process of colorizing an image? And how do you? And the second question is, how do you collect all the single frame because they are in parallel to put them together? How do you recover their order?
Oh, okay. So you're asking how we kind of stitch them back together again? Okay, so we use OpenCV to chop up the frames. So we cycle through each frame and take that out, and we collect the image data for that. Then we colorize it, and once we've colorized it, we get image data back, and then we can use FFmpeg to stitch them back together again. Was there a first question as well? What?
Which is the impact of putting so many colors, if an image will have so many colors to put together in the colorization of the image?
Yeah, well, interestingly, because we're using a convolutional neural network, it doesn't make that much difference on how big the image is. In fact, bigger resolution images work better because we've got more data to play with. So yeah, it scales up pretty well.
Sorry, I've seen that the static pictures that, for example, the dog you sent was the output, the colored output was pretty realistic, versus the video was a bit more bit like monochromatic. Does it depend on the amount of black and white information that you have in each pixel for the original frame?
Yeah. So the problem which we did have with the trailer was that the trailer was quite low resolution, and it was also quite dark at the same time. So there wasn't much. If it was a really bright video of, say, a dog running around outside a tree, it would colorize that really well. But because it was dark and it was quite low resolution as well, the network had a bit of a job coming up or working out what to do. So that's why it was slightly red. Yeah, cool. Nice.
Okay. When you transform a complete movie, you do every frame independently, right? Couldn't you learn from the previous image? I mean, a movie is not...
Yeah, so that's what we're doing with recurrent neural networks. That's what we'd like to do. But the problem with that is that you have to train it for a lot longer. So this was trained on 4.5 million images. But you'd have to train it on 4.5 million videos if you wanted to use the recurrent neural network, which poses a barrier.
Is there any way you can get the previous frame to feed on some information into the next one? Because you're just stitching frames together as entirely separate images, so it could decide that the grass is a different color in one frame to the next frame.
Well, that, we're thinking about that. That's why we said with running a 3D Gaussian blur through all of the frames, if you ran it with a really thin Gaussian kernel, you could not lose too much in terms of image quality, but between frames it would blur the changes in an image. So if it said the grass was pink in one frame, but all the other ones said it was green, then the Gaussian blur would kind of average it out slightly so that you end up having a more consistent color.
Yeah, we are like... Are you? Yeah, sure.
So great job, guys. I really like how you've put this together. It's really amazing. But what if we want to find out more? We want to try it out for ourselves. Are you going to do a write-up, or what would we do?
Absolutely, yeah. We're going to do a blog post, hopefully by Friday. We'll get that out. You can follow us on Twitter. We'll post it on there. Or openfaz.com if you want to find out more about Faz. The community is awesome around Faz. So yeah, definitely get in touch. And you can follow along on Twitter or everything. And yeah, the blog post will be out soon.
Thanks.
Yeah, a hand of applause again. Very nice talk.